Alright, so this is a fairly exciting lesson. In all the stuff we've done in this chapter so far, we've sort of dealt with the idea that we're finding out something converges or diverges, but we haven't been able to figure out what it adds up to, except in two cases, geometric series and telescoping series. And this lesson is kind of not going to be any different. I'm not going to find out exactly what something adds up to, but when you're working with an alternating series, it turns out there's actually a theorem for figuring out what the remainder is if you stop the series after a certain period of time. So first, a bit of notation. If we have some infinite series, you know, the sum on n equals 0 to infinity or something of some series, if it converges, we're going to say it's equal to s, right? S is sort of the infinite summation, right? So this is the infinite sum, right? But another notation that we picked up at some point was the notation of s sub n. And s sub n was a partial sum. It was the nth partial sum. And what s sub n represented is it basically represented the sum, and I have to use a different letter now. Let's say I equals 0 to n of a sub I. S sub n was basically a sub 0 plus a sub 1 plus a sub 2 all the way up to a sub n. S sub n was sort of the summation of the terms up to the nth term. Now, the next thing I'm going to write down is not going to be surprising, right? Not going to be surprising at all. I'm going to say that the infinite sum, the whole thing, if you added up infinitely many terms, that infinite sum would be equal to the partial sum plus some remainder, right? So we have the partial sum plus some remainder. And the reason there's a sub n there is that the remainder would be different depending on where I decided to cut my series off. I mean, one way of thinking about this is that we could say the infinite sum would be the 0th term plus the first term plus the second term plus the third term, and maybe somebody would decide to stop there. That would be their s sub n, and if that was the case, then their remainder would be the 4th term and the 5th term, and on and on and on forever. Right? That's what it would look like if you stopped and looked at the n equals 3 partial sum as what you were going to work with, and then took everything past that to be a remainder. So again, there's nothing surprising about that. It's just saying, hey, if you decided to stop somewhere, if you stopped right here, you would have a remainder, and you would have what I would call an approximation, right? And this remainder theorem is basically getting at how good is your approximation. If you stop at the 4th term, how far off are you going to be from the infinite series? And not surprisingly, there's a theorem for this, right? The theorem that we're going to have for this, and this is amazing. This is just fantastic. In a convergent alternating series, r sub n, the remainder of the thing, I suppose I should say the absolute value of the remainder. The absolute value of the remainder is always less than the absolute value of wait for it, the next term in line. Which is like awesome, right? It means suppose that somebody wanted you to add up some whole infinite series, and you're like, dude, I don't want to do that. I don't have time for that. I don't know how to do this. I'm just going to add up the first 4 things. Like, how bad could that really be? Well, I can tell you exactly how bad it would be. That. If you add up only the first 4 terms, then the worst off, like the furthest away from the infinite sum that you're going to be is whatever that next term in line is. We're going to look at some examples of this now. I think the examples will sort of serve to make this clearer. So in this first example, we're given a convergent infinite series. And if you want, you can take a minute to make sure that it converges. But we can basically tell it converges because of the alternating series test. This clearly makes it alternate. The denominators are getting, the expressions are getting smaller, and they're also tending towards 0. So it converges by the alternating series test. We're being asked to find an error bound for using the sum of the first 6 terms as an approximation for the infinite summation. An error bound is basically a number that you know that your error will not be bigger than. So we learned in the previous problem, rather in the previous slide, that the remainder after adding up the first 6 terms, R6, will be less than or equal to, or less than, the absolute value of the 7th term in the summation. Okay. So if we want to find an error bound, all we need to do is say that R, the real remainder for the first 6 terms, will be less than, and we can put 7 into this. Given that I'm doing absolute values, I don't need to do the alternating part on the top. I can just do 1 over 7 squared plus 3. The remainder for the first 6 terms has to be less than 1 over 49 plus 3, so 52. And so we can use 1 over 52 as an error bound for this approximation. It means whatever I get from adding up the first 6 terms, whatever I get from, plugging in 1 and getting positive 1 over 4, minus when I put in 2, I'd have 1/7 plus. If I did that for the first 6 terms, 3, 4, 5, 6, this is the furthest that can be away from the real infinite sum, which is kind of amazing. It's kind of awesome that adding up only the first 6 terms will get you at most this far away from what the real entire infinite summation is. And that's sort of the way that this alternating series form with the remainder works. So here we have another example of what these problems can look like. Instead of them asking for an error bound, sometimes they'll give you the error bound. They'll say, hey, we want to have an error that's less than 0.01. And they're going to ask how many terms of the infinite series would you need to use in order to be that close. And this is, almost a more reasonable question. You could, presumably imagine that somebody would want to say, hey, I want to know what this whole series adds up to. And I know I may not be able to find out exactly what it is, but if I could be close, if I could be within this amount of error, that would be great. And so they would want to know how many terms do you need to add up in order to get that. Right? So I'm sort of going to approach it the same way I did before. I'm going to look at this and say, well, I need my remainder after the first k terms. I need that remainder to be less than 0.01. Okay? But we know that our remainder is actually supposed to be less than the next term in line, right? So what we could do is we could say, I need to find the a sub n plus 1 term. Which of those terms is going to be less than 0.01? Remember, the idea here is that we know that our remainder is less than the nth term. It's less than the absolute value of the n plus 1th term. And so the idea is if I can make sure that the n plus first term is less than 0.01, that will ensure that the remainder will be less than 0.01. Okay? So now all we need to do is come up with an expression for what this thing is, an expression for what that a sub n plus 1 is. Right? So what I'll now have is I'll basically have 1 over n plus 1 squared plus 3n plus 1 plus 5, and I need to force that to be less than 0.01. And it's often helpful to sort of think about that as a fraction and to think about that as 1/100th. Now, you could move things around. You could solve this algebraically. I find a lot of times that the easier way to do this is almost to sort of take a guess and check approach. It's often quicker unless the expression that you're working with is a pretty simple one. So what I often like to do here is just sort of say, let's try like 8. What would happen if I looked at, the sum of the first 8 terms here, right? My remainder here would end up being 1 over 9 squared plus 3 times 9 plus 5. And so here that remainder is 1 over, it's your 81 plus 27 plus 5, so that's another 32. So you're looking at 1 over 113. Is that right? Yeah. 1 over 113. And so the idea here is, yay, 1 over 113, that's definitely smaller than 1/100th. So the 8th term might be okay, but what if we went too far? We should check. I don't need to check the 9th term because I'm sure that the 9th term is going to be even smaller, but we should go back and check, was the 7th term small enough? If the 7th term was small enough, then great, I can add up only the first 7 terms. So that would be 1 over 8 squared plus 3 times 8 plus 5. That would be 1 over 64 plus 24 plus 5, which is, that's your 88, that's 1 over 93. Well, 1 over 93 is not smaller than 100, So unfortunately, the n equals 7 term doesn't work, and the n equals 8 term is the smallest term that would work. So the last thing we have to do is we have to sort of go back and look at this thing and sort of see, what the question was asking for. How many terms of the infinite series below would be required? Well, we would need to do the sum from n equals 1 up to 8. And that's what we figured out, that n value was going to be 8. So since we're going from 1 to 8, the answer is that we would need 8 terms. The reason you always want to go back and look at this thing is if this thing had started at 2, well, then we're only going from 2 to 8. That would be 7 terms. If it had started at 0, then we're going from 0 to 8, and that would be 9 terms. You really have to pay attention to where the series is starting in order to know how many terms you're using to get an accurate approximation for your series. Alright, so I have one last example of how this alternating series error can be used. In this problem, you're being asked to use the first 3 terms of the infinite summation below to show that the infinite sum cannot be equal to 7/12. So what we're going to do, they ask us to use the first 3 terms. We're going to write down the first 3 terms and sort of see what that shows us, right? The sum of the first 3 terms would be the first term. The first term is 1 over 1. The next term is minus, we've got 1 over 2, plus the next one we've got 1 over 3. Okay? So we could take these 3 terms, we could add them together. If we get a common denominator of 6, we'll have 6/6 minus 3/6 plus 2/6. The sum of the first 3 terms will be 5/6. So this is my initial approximation, right? So this is the sum of the first 3 terms, and now the question is, how far off could this approximation be? How bad could how far away from the real value of this infinite sum could we possibly be? Well, we know that the remainder from those first 3 terms has to be less than the next term in line. And the next term in line, the first one that we didn't include, was 1/4, right? So my remainder has to be less than 1/4. And what that means is, it means that the real value of the infinite sum basically has to be less than 5/6 plus 1/4, and it has to be greater than 5/6 minus 1/4. Again, imagine that this is my approximation. I can be at most 1/4 above that, and I have to be at least 1/4 below that. So that the infinite sum has to fall somewhere within that range, right? So all we have to do now is simplify these things. My actual infinite sum has to be less than, and we can base this on 24ths now. This would be 26 24ths, and this one over here would be 14 24ths. And those can both be reduced. This one here is going to give me 13 12ths. This one over here will give me 7 12ths. And so, again, I have this idea that my value of s has to be in between 7 12ths and 13 12ths. And the question we were given was to show that the infinite summation cannot equal 7 12ths, and we've effectively done that. We've effectively shown that based on just the first 3 terms, the sum has to fall between those 2 values. That means that the sum can't be 7 12ths. In fact, it has to be strictly somewhere in between these 2 values based on the first 3 terms. We could get even more accurate if we wanted by going and adding the first 4 terms, or 5 terms, or 6 terms, or 7 terms, but in this case it was enough for us to just add the first 3 terms together.